Have you ever wondered what the universe is made of? Well, you're not alone. Philosophers have wondered that for ages and taken a lot of guesses. But since the scientific enlightenment, and through the study of physics in particular, a lot of progress has been made on the subject. Nobody has all the answers yet, but I want to share with you some of the really mind-blowing insights that physicists have had throughout the ages on this question, and how studying physics has radically altered our understanding of what the ultimate building blocks of reality might be. Historically, philosophers have taken three approaches to this. Maybe the universe is made out of matter, and mind is just something that somehow emerged out of matter. That's materialism. On the other hand, maybe mind is more fundamental, and matter is just a projection of our minds. That's idealism. Or how about maybe the universe is just made out of two totally different substances, mind and matter. Neither one reduces to the other. Well, of these three, materialism seems to have held up the best in the face of scientific evidence. In today's modern world, both scientists and philosophers tend to agree that materialism ended up being the closest to the truth. But what if there's a fourth option, none of the above? Neutral monism is the idea that both matter and mind reduce to something else, something more fundamental that the universe is made of, something nobody ever thought of before. Let's go all the way back to Aristotle, one of the world's first great philosophers. Aristotle thought that you could separate everything in the world into two basic categories, animate and inanimate. Animate things were self-moving, while inanimate things could only be moved by other animate things. His distinction was based on his own theory of physics. He thought that an inanimate thing needed an animate prime mover to start it moving, but not only that, but to keep it in motion. If the mover stopped moving the inanimate thing, it would soon come to rest in its natural place. For example, if you kick a rock, it moves for a little, but then very quickly it settles down to rest. That's because rocks are inanimate. Make sense? Of course, it's common sense. The problem is, it turned out he was wrong. The truth is, that's not how physics works. Today we know many examples that just don't fit into either of these two categories. For example, robots. Are they animate or inanimate? Sponges at the bottom of the ocean. Technically, from a biological perspective, they're considered animals, but they don't move. They just sit there. They sway a little bit like plants, but they're fixed to the bottom of the ocean. But wait, what was wrong with Aristotle's physics? Well, basically, he didn't know about relativity. A lot of people think that Einstein discovered relativity, but actually, the original principle of relativity was discovered by Galileo right at the dawn of the Enlightenment. Galileo realized that motion is relative to the observer, so that there really is no such thing as absolute rest. If a sailor's on a big ship out at sea and he does a physics experiment below deck, assuming the sea is calm enough, there won't be any way for him to tell whether the ship is moving or if it is moving, how fast. Relativity was very important to Galileo because it gave him a good response to all the people in his time, such as the Catholic Church, who thought that Copernicus' theory that the Earth went around the sun was absolutely crazy. They would say, "But silly Galileo, don't you think that the entire Earth were moving through space? We would all lose our balance and fall down. Wouldn't we feel the motion? Obviously, common sense tells us that the Earth is at rest." But Galileo said, but there is no such thing as absolute rest. All motion is relative. So even if the Earth is moving, we wouldn't feel it. We wouldn't have any idea. Much later, Albert Einstein expanded Galileo's principle of relativity. He said, not only is motion relative, but even things like space and time are relative, and whether events are simultaneous. All of these things can only be measured relative to the observer. But ironically, even though there isn't any absolute zero velocity, like there is an absolute zero temperature, it turns out that there is an absolute max velocity, the speed of light. So much for common sense. So if materialism says that the universe is made out of matter, what is matter? Aristotle thought that matter was a fluid substance, something continuously and infinitely divisible, like liquid. But as everyone knows today, matter is made out of atoms, and those atoms are made out of smaller subatomic particles. As Einstein discovered, the energy of a particle can be broken down into two parts. There's a part we call the kinetic energy, which has to do with how fast a particle is moving, and then there's another part called the rest energy, also known as mass. Because of relativity, the total energy of a particle is relative to the observer. How much energy it has is determined by what reference frame you measure the particle from. When viewed from within its own reference frame, where the particle is seen as being at rest, the kinetic energy is zero, so its energy and mass are exactly the same thing. In many ways, mass and energy are equivalent. There are two types of particles in the universe, fermions and bosons. The fermions are what makes up the matter, and the bosons are what makes up the less tangible stuff in the universe, the stuff we don't usually think of as matter. For example, light, radio waves, microwaves, other kinds of radiation, the forces of nature, and of course, the famous Higgs boson. But wait, it gets crazier. About 10 years after Einstein published his work on special relativity, a mathematical genius named Emmy Noether proved a completely revolutionary theorem known as Noether's theorem. Not only is matter a type of energy, but energy itself is just a special kind of symmetry. A lot of people get confused about this. They hear the word energy and they think that it's a substance, kind of like the old material or spiritual substances that the ancient Greeks believed in. But no, it's not like that. Noether's theorem shows that all of the forces of nature, as well as anything which would usually be called a conservation law, like the conservation of energy, are really just symmetries. Noether's theorem says that for every symmetry in physics, there's some mathematical quantity called a conserved charge. For example, the conserved charge for electromagnetism is electrical charge. For rotational symmetry, it's angular momentum. For time translation, it happens to be energy. Time translation is the symmetry which says that the laws of physics are the same in the present as they were in the past or the future. So long as that's true, there will always be a conserved charge that we call energy. The most accurate and precisely tested and confirmed scientific theory in all of history is quantum field theory. Quantum field theory is what physicists use to describe the microscopic world of subatomic particles. Before quantum field theory, it was generally assumed that elementary particles were the fundamental constituents of matter. But what is a particle? It's actually nothing like the classical picture of a particle that came before quantum field theory. Today, we know that particles are actually just quantized waves that propagate on quantum fields. Each elementary particle has its own field, and the fields themselves are much more abstract entities, things that mathematicians have been familiar with and have studied for a very long time. Scalar fields give rise to the Higgs and the inflaton. Spinor fields give rise to quarks, electrons, and other leptons. Vector fields give rise to photons, gluons, and other gauge bosons. And the only known tensor field, the metric tensor for spacetime, gives rise to the graviton, the particle that transmits gravity via the curvature of spacetime. The point is that these things look a lot more like pure mathematics or geometry and a lot less like material substance. For example, you can visualize a vector field by picturing a giant field of arrows that point in a particular direction at each point in space, or a scalar field is just a number that gets attached to each point in space. Richard Feynman invented a notation you may have heard of called Feynman diagrams to visualize what happens when particles interact with each other. For example, the diagram here shows two electrons interacting by exchanging a photon. The truth is, all of the so-called forces of nature are really, in a sense, illusions. What really happens when two electrons repel each other is not that some mysterious force acts at a distance between the two, but that one of them emits a photon and the other absorbs it. Each of them adjusts their energy and speed accordingly. The shift in paradigm here is very similar to what happened when Einstein realized that gravity was due to the curvature of spacetime. Isaac Newton had previously assumed that gravity was a force that acted instantaneously at a distance, but it turned out that that was just as much of an illusion as the apparent force between these electrons. Before I wrap this up, let me tell you about one more mind-blowing thing, virtual particles. Virtual particles are the name given to the intermediate lines on Feynman diagrams such as this one, where a particle gets emitted and absorbed in such a short amount of time that there's no way it could ever go into an actual physical particle detector. Physicists usually differentiate between these virtual particles and the particles that can go into physical detectors, which they call real particles. But the math which describes them is nearly identical. And without virtual particles, it would be much more difficult to visualize what's going on at the quantum level. In the mid-1970s, several physicists, including William Unruh, as well as Paul Davies, Stephen Fulling, and Bryce DeWitt, started to realize that the implications of relativity went one step further than was previously realized. Remember how Aristotle's distinction between animate and inanimate turned out to not make much sense because motion is relative to the observer? Well, a very similar thing happens when you try to make a distinction between real and virtual. Quantum field theory was originally worked out from the point of view of an observer in an inertial reference frame. That means someone who's either at rest or moving at constant velocity. Remember, because of relativity, those are actually both the same thing. But what happens if we look at the same quantum fields but from the point of view of an accelerating observer? Well, it turns out that even the concept of empty space, which physicists call the vacuum, is relative to the observer. What one observer sees as empty space, in other words, space containing no real particles, a different observer will see as a thermal bath of real particles. Where did these particles come from? Well, to the first observer, they were just virtual particles, so they were invisible. But the change in perspective changes the definition of what is considered real. Some virtual particles become real particles, and some real particles become virtual particles. Just like motion, space, and time, whether a particle is real or virtual is observer dependent. This is commonly referred to as the Unruh effect. So the truth is, I lied to you earlier when I said that there is an absolute zero temperature. Temperature, like everything else I've mentioned, is also relative to the observer. This is another consequence of the Unruh effect. What one observer measures at being at zero temperature, another will measure at being at some finite temperature. Sometimes when I think about all this, I think, man, if only Galileo or even Einstein were still alive to see just how far their original theories of relativity have come. So if you're a geek or a science enthusiast who reads a lot of books or news articles on physics, you might be thinking to yourself, why have I never heard of the Unruh effect? Like Noether's theorem, I'm not sure why it hasn't gotten more attention in the media, but if you're a physics geek, you probably have heard of one version of the Unruh effect, and that's Hawking radiation. Hawking radiation is radiation, a heat bath of particles, that comes out of a black hole. Before Stephen Hawking, it was assumed that black holes were always measured to be at zero temperature, but this is only true for someone falling into a black hole. One of the most important parts of Einstein's general theory of relativity is known as the equivalence principle. The laws of physics for an accelerating observer are locally indistinguishable from the laws of physics for an observer in a gravitational field. Just as there's a difference in perspective between an inertial observer and an accelerating observer, there's an analogous difference in perspective between an observer falling into a black hole and one who's observing it from a safe distance. To the observer falling into the black hole, space looks empty, and the only particles there are the invisible virtual particles that make up the vacuum. But to the distant observer, actual real particles are being emitted from the black hole, and it will be measured as being hot. So there's a whole lot more that's been learned about the universe beyond what I've told you. We're just scratching the surface here. I haven't even gotten into quantum entanglement, the holographic principle, string theory, or black hole complementarity. But just based on what I've given you here, which takes you through the end of the 1970s, I hope that I've made a good case that whatever the universe is made of, it's quite different than what common sense would have suggested, and certainly way more interesting. The original notion of a universe that can be easily described from some third-person perspective, God's eye view, which anyone sees as the same, has been replaced with something that looks very different from different points of view. I've given several important examples of this via relativity, but there's even more examples in quantum mechanics I haven't even bothered getting into. Does this mean that we have to give up materialism? Does it mean that we should go back to dualism or idealism? A lot of the answer to that probably depends not on physics, but on having a better understanding of consciousness. In other words, things that neuroscientists, psychologists, and philosophers of mind study, not physicists. But I think what physicists can say for sure is that if we do want to hang on to the word materialism, we're going to have to radically redefine it to mean something pretty different from what the ancient philosophers had in mind. Some modern philosophers have switched to the term physicalism instead, but personally I find this term equally inappropriate. All of the physical things we know of in the universe are in fact made out of things that seem to have very non-physical qualities to them. In fact, everything seems to be made out of something more like pure information or mathematics. There's still a lot more work to be done in order to fully understand this, and I don't want to dogmatically push anyone in one direction or another, but personally I do think we should consider moving beyond materialism to something more like neutral monism. Thanks a lot for watching my presentation, and I hope you learned something.